Now let's look at another heat capacity problem example. And in this case, we've got a 200.0 gram tin rod dropped in, it's at 178.0 degrees Celsius. It's dropped into a vessel containing 100.0 grams of water. The final temperature is 30.5 degrees Celsius. And the heat capacity of tin is that, and the heat capacity of water is that. The temperature of the water was initially, and that's what we're going to be looking for. So it seems that we're looking for water, and what we've got the most information about is going to be the tin. So that seems to be the best place to start. So what we're going to do here is we're going to try and figure out the amount of heat that was going to be released by the tin. Now what's going to happen here is we can see that the temperature of the tin is going to go down. It's going to be at 178.0 degrees first, and then at some other point it's going to be 30.5 degrees Celsius. So where did all that temperature go? Well, the temperature went down because the heat of the tin was released into the water. So we know that the temperature of the water is going to go up, and that's going to be its final temperature right there. It will be 30.5 degrees Celsius. Alright, so we start off, we've got the Q of tin. That's what we're going to find out first. And we're going to measure that by the mass of tin times the heat capacity of tin. Oops. Times the change in temperature of the tin. And we can get that by doing 200.0 grams times the heat capacity and notice I'm using my units here as well while I'm doing this. Now the change in the heat, the change in temperature of the tin is going to be 178 minus 30.5 degrees here, and that's going to be 147.5 degrees. Now just a note on significant figures. With the temperature, that's okay because it's one decimal place and one decimal place. So this comes out to one decimal place as well. Now I do this and it comes out to be 6195 joules. Now another note about significant figures is that I'm not going to change the significant figures here until the end. I will do some adjustments later, but for now I want to keep this value as it is because I'm going to be using that in a multiplication and division in the next step. The only time I really have to worry about significant figures is if I'm mixing operations, if I'm doing additions and subtractions and that's affecting things. As it is, this one has 4 significant figures and this actually has 3, so I'm going to end up getting something that is it's going to end up really with 3 significant figures, but I'm going to carry it out to 4 for now because we're not at the end of the problem. Alright, so now I'm going to figure out what's going on with the water. Now we know that the Q of the water is going to be the mass of the water times the heat capacity times the change in temperature of the water. Now we know that this is also going to be the heat that's actually absorbed by the water. So I'm going to be able to find out the temperature change of the water, and the temperature change will be 6195 joules divided by the mass of the water, which is 100.0 grams, times the heat capacity of the water, 4.18 joules per gram per degree Celsius. And that's going to come out to be the change in temperature of 14.8 degrees Celsius. Now in this case it is necessary to take significant figures into account because in the next step I'm going to be using this in an addition subtraction. So I have now taken this down to three significant figures. I've got 14.8 degrees Celsius. What does this represent? Well, it represents the change in temperature of the water. Now we've got to figure out what happened to the temperature of the water. Did it initially go up or did it go down? Now we know that the final temperature was 30.5 degrees Celsius. We also know that the temperature of the tin went down, and it went down from 178.0 degrees to 30.5 degrees Celsius. Naturally, it must have been that the water must have gone up in temperature, which means the initial temperature of the water would have been 30.5 degrees Celsius minus 14.8. 14.8 degrees Celsius representing the temperature of the water, change in temperature of the water as it went up in temperature. And that comes out to be 15.7 degrees Celsius. So that was the initial temperature of the water, and that makes sense. It went up by 14.8 degrees to become the equilibrium temperature that we observed in the problem. And again, with the significant figures, you can see we've got 1 decimal place and 1 decimal place, which is going to come out to 1 decimal place.